Hello, hello. I hope you can all see this. I hope you had a brilliant break, and I hope you're ready for some more exciting algorithms. Um, I'll do a long recap today because it's been a long break and we have some announcements to catch up. So just while we're settling in, I wanted to ask a little icebreaker again. If you had to summarize your break in one word, what would that word be? Great is really good. That sounds like you managed to have an actual break. Um, Not everyone. Yeah, same here. Insufficient. Yeah, 3 weeks can be fast. I had lots of good plans, and then I was sick half of the time. Nothing really bad, but it wasn't as productive as I was hoping. So I feel for you. Okay, but the majority says great. That's a good thing. So with that, let me move to the announcements. We have a couple of deadlines coming up this week, so I just wanted to list these again. And of course, you noticed that we had the deadline choker vote. So the winner was the bamboo puzzle. It was originally due also on Friday, but now we pushed it forward. Just to point this out, if you go to the home page of the course in Canvas and you scroll down all the way to the bottom, or it's in the right, depending on how big your screen is, you always see the upcoming deadlines as they're registered on Canvas. So the gray ones are already passed. But you see the video presentation, which is essentially due in an hour. And I hope very much that you're not working on this now, but instead focus on the very cool suffix tree tricks I'm about to show you today. And the two class tests are still due on Friday, but they were already running for a long time, so and shouldn't take too much effort to finish. So maybe these are not as bad. And then the programming puzzle is moved to next Friday. So you have some more time on playing with the bamboo cutting problem. As always, if you have any questions about organizational things or material, please use CampusWire. The platform has been a bit more busy lately, but it could be much busier. It can cope with many more of your questions, and I'm sure these will become a little more urgent as we move closer to the exams. But these are still a couple of weeks down the road, so let's not spoil our good mood with talking about exams today. So these are the upcoming deadlines. I've seen a lot of people have uploaded the videos already, so this is probably fine. I'll start marking these right away, but we'll definitely need a couple of days, and this week is pretty full, so don't expect results about this very soon. Once the videos are marked, I will release the marks on Canvas. So as soon as you see marks on Canvas, these are the actual marks, and they're final as they get for continuous assessment. I'll also try to leave some feedback on Canvas as well. So set up a notification for these. The last thing I wanted to say is the tutorials by request, people liked Ben's slides, and you haven't got a chance to see Ben's slides for sheet 4. So we decided, because I'm also half a lecture behind, nothing severe, but it meant that it would have been a bit of a stretch to push the exercises I would like you to work on sheet 6 are about things that we just covered today. That would leave you little time on working on those before you go to the tutorials. So what we do instead is we use this week's slots for sheet 4. That was about the string matching problems, not the parallel one, the standard one, sequential. If you're already very familiar with these, maybe you don't need the Friday sessions and you have some extra time on working on other things. but I think many people found Ben's slides very helpful. So we do this this week, and then all the other tutorials are just moved one week past, which doesn't really affect anything because, as I noticed, I don't really have anything planned for the last unit, so it all works out nicely. So much for that. Let me switch one more time to this little thing. A few more votes for busy, I think. Boring sounds actually great. That means you were at least not working all the time. Of course, it's not great if you're bored. But that means you're even more looking forward to lectures, which is a good thing after all. Okay. With that, let's move our attention back to suffix trees. Remember, zooming out a little bit, we're in Unit 6, which is about text indexing. We left the problem of string matching, where we are given a small pattern and we try to find that in a big text without knowing the text in advance. And now in the text indexing world, it's a little the opposite. We have a long text, but we can pre-process the text. We can take our time and spend effort on the text. But then when someone asks, where do all these patterns occur, we want to answer these questions very quickly. So it's more like a search engine, or more like a search in a, I don't know, encyclopedia. Many websites use techniques like this. The suffix trees are specifically interesting if it's textual data that doesn't have words. It's often enough for natural language text to search for words. We talked about inverted indices briefly. But these approaches are very limited, even though they might be effective for things like actual Wikipedia. Yeah, for things like bioinformatics applications and many other cases where there's no obvious word boundaries, or you want to search for arbitrary phrases, you need heavier machinery. And the suffix trees turn out to be the ultimate solution to many of these problems. I showed you this quote from Dan Gusfield's book about Don Knuth, who conjectured that a certain problem, finding the longest common substring in a set of strings, would not be possible efficiently in linear time. And he was proven wrong by the invention of suffix trees eventually. So let's recap this important definition. What is the suffix tree for a given text? No, I'll leave it here. It's a bit small, but maybe it's fine. So a suffix tree for a text is just a trie over all the suffixes of the text. We always append this end of word marker to avoid that any suffix is a prefix of another suffix. So when the text originally has n characters, we're actually constructing a text of n+1 characters by adding this, and then we take all the suffixes of this extended text and make a trie out of this. And it's a compact trie, which means we have eliminated chains of unary nodes. So here's an example with my favorite string for that first part, banana ban, because it's very self-repetitive. And you see, you find for every suffix in the text, you find a leaf in the suffix tree, and there's a path labeled with exactly that string. You will also remember that this is not how we store suffix trees for the computer. They actually look like this. So they're fairly memory efficient. For each edge, we store one character, and for the leaves, we just store a number. We'll talk about memory usage in a different sense. If you just draw it like this, it's fine. The total space is linear in the length of the text. So you need a constant number of bits for every position in the text. It will turn out that this constant is fairly big, but we'll come back to that. We've seen we can build these naively, but then it takes a lot of time, and it's not at all interesting for all the problems in stringology, like finding the longest common substring between a set of strings. It's only interesting if we can construct the suffix tree efficiently. And one of the landmark results in this area is that you can construct the suffix tree in linear time. And I will actually show you how to do this today and tomorrow. It's probably the most complicated algorithm we look at, also the most amazing one. But it's also great because it just builds little steps on top of each other. None of these steps is really impossible to understand. It takes a bit of caffeine, as I warned you ahead of time. But it's totally doable. But then once you piece all these little steps together, you get this amazing result that was not at all obvious, even to very smart people at the time, that this would be possible. Okay, enough for advertisement here. So that's what we wanted to do, and I've showed you a handful of applications of suffix trees. In particular, we're looking at text indexing. So pre-processing a text and then finding all the occurrences of a given pattern. We found that this can easily be done with suffix trees. We also found that we can find in one string the longest repeated substring. So any string that appears as an identical copy in 2 positions is such a repeated substring, and we want to find the longest one. Because, well, every single character is usually repeated. Sometimes that's not so interesting, but the longest one is significant. And again, suffix trees were basically the solution for this. And we even had a very simple algorithm for this. It was an important notion that I want to repeat here is the string depth of a node. Usually the depth in a tree is just the number of edges we have to walk down from the root. In a suffix tree, there's also the notion of string depth, because some of the edges are labeled with several characters. So that's just the length of the string that you read when you walk from the root to this node. And it turns out if computing the string depths is easy bottom up, that can be done in linear time. And once we have the string depths written at all these internal nodes, we just pick the deepest of these, the one with a maximal string depth, and that corresponds to the longest repeated substring. So once we have the suffix tree, again, such a fairly sophisticated problem became very easy. Then we generalized suffix trees to a set of strings, basically by just putting them together into one big text, like so. We added new end-of-word markers, a different end-of-word marker for each of the strings. So at least theoretically, that's a very elegant solution. And then you build a suffix tree for this single text, which again is what you already know how to do. And well, with that preparation, we could eventually solve this landmark problem, the longest common substring in a set of strings. Roughly the same as the longest repeated substring. So I'll skip that part. You've seen that last time. Now we're getting closer to where we left off. It turns out for some problems on suffix trees, this is not quite enough. We need a little extra magic box. And these are constant time longest common extensions. So remember the definition of this. A longest common extension is given 2 positions in a string. Find me the maximal number of characters that I can read that are identical if I read in both positions. So it's a string that appears starting at I and starting at J. And I want to know how long is this string so that the 2 are the same. That's the longest common extension for starting at these 2 positions. And well, we looked a little bit. So here again, this is something we'll build on later. So let me go over this again slightly more in detail. The longest common extension of 2 positions in the text, I and J. That is just another way of saying that's the longest common prefix of 2 suffixes of the text, namely the suffixes starting at these positions. Well, that just means I can start reading at this position up to a certain point. Strings are the same. That's the same as saying the suffix starting here, the suffix starting here. they have a common prefix. They have a certain text in common at the beginning. That's the very same thing. Why do we stress this? Well, because longest common prefixes tend to be reflected in a suffix tree in terms of an internal node. So indeed, if I have the two leaves, I and j, and here my example was with 5 and 7, I wanted to know what is the longest common prefix of aban and an. And indeed, in this case, it's just the a, because after that, they differ on the next letter. And we find that in the tree, in the suffix tree, by looking for the two leaves and finding their lowest common ancestor. That's denoted by LCA. That's this node. And that node's string depth is the length of the longest common extension. Okay, so this is something you should memorize, because it's very useful and will be used later on as well. So that's how we can make the connection between longest common extensions and suffix trees. Again, another magic box if you want for now. And we will only look into this magic black box at the very end of this module, because the content is a little more, a little hairier. This will be outside of the examination material, but it's very, very nice. A very nice data structure as well. You can do lowest common ancestors in simple ways, but the result that we need is pre-process the suffix tree in linear time, and then allow us to find the lowest common ancestor of any two leaves in constant time. So we can directly jump to this node for any pair of leaves. And that indeed requires a little extra thought, and we will come back to it. But not today. Where we left off last time, so maybe I should, yeah, at this point, let's officially start the next lecture video. So I'll slow down a little bit from now on. I know this was very fast-paced, but it was also repetition. I didn't want to not repeat these things today. Not sure how useful it was for you at that pace, but still, so it's a little bit of a refresher. You've seen all this before. And now let's take a step back, take a deep breath, and then we'll continue. We left off last time in the middle of discussing this fifth application of suffix trees in combination with longest common extensions. That is the problem of approximate matching. So instead of finding exact occurrences of a pattern in the text, we're now asking a more challenging question: find all the occurrences of a pattern in the text where the occurrence is not exact, but it might differ from the text in a certain well-defined way. And the well-defined way in this case is I want the Hamming distance between the two things to be at most k. And what that means is just there's at least at most k mismatched characters if I align the pattern at that position with the text. So again, schematically, I find a position I where I can put the pattern, and then it essentially occurs here exactly, except maybe for k positions where there's a mismatch. And if I can do this, then I say the Hamming distance of this portion of the text and the pattern is 2 in this case, because there's two places where they differ. That's a simple concept. It's probably the simplest version of approximate matching, but that's the one I mean here. So if you like, it's searching with typos, something that Google became very, very good at. And definitely people make more and different mistakes than just these replacing one character by another. So in practice, you will need more variations of this, but we'll leave it with the simplest version for now. A second thing I mentioned last time is similar to generalized suffix trees, you can also build this longest common extension data structure for several strings, and you do the very same trick. In this case, we take the text and we take the pattern, we append end of word markers, different ones for the different strings. So here, 2 different ones in our case. And then we just build the suffix tree and the LCE data structure on this combined text. And no other changes are necessary to this construction. What that means is that we can find longest common extensions where one position is in the text and one position is in the pattern in constant time. Okay. And this is, okay, let me, okay, maybe it's a good time to first recap this. I hope you couldn't see this. Now, I know you can rewind, but please don't. To wake you up a little bit, I want to ask you to check all the correct statements about suffix trees. So this is a lot of different statements, and a subset of these will be correct. This is just before we move on, before we dive deeper after this, I want to see if you're up to speed with the definitions, etc. For the Kangaroo algorithm to follow, we don't really need this, but for the deeper results after that, we will definitely need it. So it's good to ask this first and maybe discuss questions before we move on with the new material. As always, I'd like to see our 25 people roughly vote. I've seen 28 people on the word poll, so maybe we lost 1 or 2 who haven't returned from the spring break yet. But I'll leave you a little bit of time, switch back maybe, because here you can read all the answers. It's a lot of text to read, so I'll give you some more time to digest this. Okay, we have 25 votes. Thanks. So I'll show you your results. And I should probably lock the voting now. Most people remembered correctly that we have to attach this end of word marker. This one's an interesting one, and this has to do with this answer. The suffix tree is a compact trie of all the suffixes, and not a standard trie. Standard trie is the one where also the unary chains of nodes are represented as nodes. And you might remember there we had an example where essentially you need a quadratic number of these nodes for the standard trie. But the compact trie always has linear size. Because it's a binary, it's a tree with all internal nodes having at least 2 children. And we have n or n plus 1 leaves. We'll come to that. And so the number of internal nodes is at most n. It's therefore the size of the suffix tree is always linear. The quadratic is only for the standard trie. Yeah, most people got this. We don't have to store a copy of the suffix in the leaves. It's enough to store the text somewhere separately and then just store a starting index of the suffix in the leaves. The naive construction is slow. That's correct. It takes quadratic time because in the worst case, because well, we have to walk down the tree. It depends what you mean by naive construction. What I meant by it is take the trie, insert all the suffixes one after each other. Then each insertion takes time proportional to the length of this suffix in the worst case, and that adds up to quadratic in total. But it is true that we can do better. We can compute it in linear time. We haven't seen that yet, but you have seen the claim. And the last answer is almost correct, but not quite. It has n+1 leaves because we added this end of word marker. All right. Thanks for voting. So here again, the answer is for the record. If there are questions about this, please shoot them up in the Q&A now. That's a good point to clarify if there's anything unclear about this. We will build on this, but keep the pictures in mind. The details of n and n+1 are usually not that important, but of course we have to define it precisely so that we know what we're talking about. Okay, good. So now that we all remember and know what suffix trees look like, let's move on. We were in the middle of this application. We want to find the approximate matches of a pattern in a text. And what we have is this magic black box that tells us if I have a position in the text and another position in the pattern, what is the longest extension, the longest common extension at these two positions, and it can do that in constant time. With that, we can build the following algorithm, which has become known as the Kangaroo Algorithm because it proceeds in jumps. So first the picture again, and then I'll walk you a little bit through the code, but it's not really complicated code. Maybe a small sketch or an example is enough here. So we're at the position that we currently try to find. Well, at first I should say approximate matching is complicated. You can't expect to do this as fast as the exact matching. That won't work. So we're already quite happy if we can do something like the brute force algorithm, except that we don't want it to be quite as bad. Now, even a naive brute force method would need n times m here, because it's Hamming distance. So we could check each of the guesses and just count how many mismatches we have. So that's a remark that we can easily do it in n times m. Now, if the pattern has length 100 or so, if the pattern is very short, maybe that's good enough. But if the pattern is a bit longer, and people use similar ideas for bioinformatics applications where your text is a human genome and the pattern might be a certain mutation that is known to cause problems, then this mutation encodes usually a gene that can be 10,000s of characters. So m might be fairly large, and then m times m is not efficient anymore. What we will achieve is n times k, and that's a different ballpark because k is usually very small. If you want to find a match but half of the things don't really match, that's not really useful. I tend to think of k as a small constant, less than 10 or so. And then this method is very efficient. How does this method work? It's still inspired by the brute force method. We check each guess naively. So we currently try to find a match of the pattern in the text starting at position I. So we have to compare these two strings and have to check whether they have Hamming distance at most k or bigger than k. And we use this kangaroo technique to speed up this search. We take we start at position 1 in the pattern and at position I in the text. That's how this is initialized. Oh, sorry, we start counting at 0. So of course it starts at 0. That's what the piece says. And then we find the longest common extension. So we find the number of characters that match between those two. That is L. And we compute that using the LCE data structure. And now, when the LCE data structure says there's 4 matches, we already know that at position 5 there is a mismatch. Otherwise, LCE would have been bigger. So we don't really have to explicitly check that 5th character. We already know it's not the same. So we advance both our position in the text and our position in the pattern by L+1. And we also remember that we spent one of our mismatch from our mismatch budget. And then we continue the next jump. And maybe this gets us to here until we find another mismatch. And maybe this is fine because 2Ks is at least 2, and then we find a match here. So of course, where does the kangaroo come into this game? We jump from 0 to this position and then to this position. So we leapfrog over these matching parts. That's where the name comes from. How much time do we need for this? We have a loop running n times roughly for all the guesses. That's where the n comes from. And then the k comes from the inner loop because we always increment the number of mismatches. And if we have already reached k mismatches, there's no need to further compare the suffixes. There won't be an approximate match in this case. Okay. That's all I want to say about this. Right, the pre-processing is essentially what we have to do for the LCE data structure. So behind this innocent term is construct the suffix tree for the generalized suffix tree for the 2 strings, text and pattern, compute the constant time LCA data structure on top of that. Those 2 together make this longest common extension black box that's used here. So this pre-processing is linear in the size of text and pattern. But of course, it's quite a complicated algorithm that's going on behind the scenes there. Some remarks. So this is a fairly simple algorithm. People found ways to substantially improve over this. If you stay with the Hamming distance k, you can do something like this where it gets easier the longer the pattern is. That uses very different techniques than this above. And you can also generalize approximate match to something like edit distance, where you can not only replace one character by another, but you can also delete a character, or you can insert one that wasn't there before. That's a bit more flexible, a bit closer to what people might be doing when they type on a keyboard and erroneously type something different than what they actually wanted to find. And a last little application is what we've seen with the Kangaroo algorithm can also be used for matching with wildcards. So in a very simple way, here a wildcard, this is not like in Unix, the star matches a single character here. So you can see this is a choker character that you can substitute with any character, but only one. That turns out to be essentially the same question as the k mismatch problem. So you can solve it with a similar algorithm and get similar running time. That's just summing up pre-processing and the Kangaroo algorithm running time. But that's again something that is occasionally very useful. And suffix trees make this very simple. Whereas if you try to do this in a running time that's substantially less than n times m, you have to be very inventive. Let me finish this section on applications of suffix trees and suffix trees plus longest common extensions with the remark that there is a classic book that I've cited before from Dan Gusfield, where he describes over 20 of these applications, including these, but there's 14 others that are very interesting. They're more from bioinformatics that need some background to be useful, so I excluded these. But I want to stress again what a threshold concept suffix trees have been. They enabled lots of applications where each of the little application algorithms, they needed slight twists, etc., but they're fairly easy to understand. The real complication only lies in getting the suffix tree constructed efficiently. Okay, that brings me to the discussion of suffix trees as we've seen them so far. I've already made this advertisement. It was a great leap forward. They can be constructed in essentially the same time and space as storing the text or reading the text itself. Really remarkable. But they do have some downsides, and this is what we will work on next. First of all, the construction, it is linear time, but it's actually a substantial overhead in the sense that there is a constant attached to it. It's not the same time as reading the text once. It's the same time as reading the text 1,000 times, maybe. Maybe 1,000 is already exaggerating, but it's a substantial overhead. And people have worked hard to reduce that overhead. Also, the construction methods that directly construct the suffix tree in linear time are fairly complicated, both to understand and to implement. And the last point, which might be the strongest from a theoretical perspective, from a practical perspective, is that suffix trees need a lot of space. Again, they are linear in the size of the text, but there is a constant attached to it. It's not 1,000, but it's a factor 10 or so, or 20, depending on how smart you are. I think you can achieve a factor 10 if you implement it really well with low-level tricks, etc. And that already took people a lot of effort. If you do a more careless implementation, your factor will be much bigger. We might have talked about this briefly when we discussed tries already, but just remember, how do you represent a single node in a trie? It has potentially one child for each possible character. So even if your alphabet is the ASCII alphabet, the ASCII characters, so just the 128, that's our small sigma, you have two options. Either you represent the children at each internal trie node as a dictionary, then you have additional overhead to search. Say you use a binary search tree over the symbols. That then you don't have the constant time anymore. Or you represent the children in each node as an array with 128 entries, and there's a pointer to that child if that exists and null otherwise. But then you would have an array of 128 pointers per internal node. So that's substantial overhead, and there seems to be no easy way to avoid any of these downsides. Not both at the same time. So suffix trees are great in theory, but they suffer from this overhead in practice. And that's what has stopped people using them in many applications. All right, any questions about the applications of suffix trees? Then please post them now. What we'll do next is we'll move away from suffix trees for a little bit, then to come back, and eventually you will see how to construct them in linear time based on the next ideas. But we will leave the applications for now. So if you have any questions that we should discuss about the applications, these different string problems, then now is the time. If there are no questions at the moment, then let's move on to the next exciting topic. In this next subsection, I want to introduce suffix arrays. They're very related to suffix trees, but much simpler, both to understand and, as we will see, to compute. Nevertheless, they capture the essence of what makes the suffix trees magic, and they will eventually solve this problem of constructing suffix trees in a very elegant way by using suffix arrays as an intermediate result. So let's see what suffix arrays are about. One observation that we can make in a suffix tree is if, so one assumption here is that I'm ordering the edges going out of an internal node by the lexicographic order of the first character. So here the dollar is always the smallest in our alphabet that comes first, then A, then B, then N. And the same is true at every node. B comes before N. If I do this and I look at my list of leaves, I notice that the leaves list the suffixes of the text in sorted order. They're sorted lexicographically. Dollar is the smallest, then comes A-ban, then A-n, and so on and so forth. Okay, that's a simple observation. But what we'll do now is essentially ignore all this part on the left, throw away the entire tree if you want, and only keep this list of sorted suffixes. That is the suffix array. More specifically, we store an array L, and I tend to think of L to stand for leaves. That's the leaves of the suffix array. And remember okay, let's do the algorithm first. But remember that the leaves actually store a number, not the string really. Right, this would be, I don't know, whatever the last position is, a 9. So these would actually store the starting index of that suffix and not a string, which also means L is just an int array. It's an array of numbers. Okay, much simpler than a tree in terms of how to represent it. What can we still do if we don't have access to the suffix tree, but only to this array of leaf entries, the numbers in the leaves in left to right, well, left to right if you draw the tree in the normal way, top down in my way of drawing it. What can you do if you just have the sorted leaves? It turns out that's definitely enough for string matching, because we can use binary search for a pattern. Suppose we want to find if the text banana ban contains Anna, the Spanish Anna. How would we do this? Well, we do a binary search for Anna where we fill it with dollars in case of doubt. And, well, how would this work? We would probably start comparing here. Anna is smaller than this because the first character where we have a mismatch is the N and dollar comes before that. So initially we had it's somewhere here. Now because it's before that, we know it's somewhere here. And then I don't know how the type breaking is implemented. Maybe this is the next to compare. So we compare this with Anna. So here the result was search in the upper half. Here the result is Anna comes after ab. So we go down. And that means we have narrowed down the interval to these two nodes. And maybe here we would compare with this next. And then Anna actually comes after this. And then we're left with this single position. And now what we do is just check if Anna is a prefix of the suffix at this position. And if that is the case, then we have an occurrence of the pattern. And if not, we don't have an occurrence of the pattern. And so with a simple binary search, we can solve the string matching problem. So what we need for this, the complexity of doing string matching with a suffix array is log n. That comes from the binary search. We have to cut the range in half log n times, or roughly log n plus 2 for rounding. And each of these comparisons, whenever I ask, is Anna smaller lexicographically than this text, each of these checks needs actually m text character comparisons, because we have to scan from the left, or in the worst case, m character comparisons, because we have to scan the pattern of the text from the left. That way. All right. So we can search for occurrences in the text. And another little comment that I want to make is you can actually find all occurrences in the text just as easy. There you just do 2 binary searches. And for the second one, you use Anna with, I don't know, another symbol that is bigger than everything in the alphabet. So it's just you search again. In this first binary search, you pretend that the next symbol of the pattern is coming before all the actual symbols. And in the second search, you pretend it's coming after all the symbols in the alphabet. So what you will find is the first position ends, the first search ends here, and the second search ends here. And that gives you a range, and all the leaves in that range, if it's non-empty, start with Anna. So it's even, in a sense, it's much easier with suffix arrays to solve these variations of the problem. Find me the first match, all matches. These are fairly easy to do because you can conveniently find all matches grouped together like this. But that's more of a side remark. So we define the suffix array as this leaf array. So here it is. As I said before, the actual value stored in the suffix tree is not the string, but the starting index. So the suffix array is just this list of numbers. And the rth entry in the suffix array is the starting index of the rth smallest suffix in lexicographic order. Okay, that's the suffix array. Let's see if you digested this. Where's my question? So similar to before, it's a multiple choice. You can take as many answers as you want. And some of these are correct. Not all of these are correct. And I'll give you a minute to digest all these statements. I'll wait for the 25 answers again. I know these questions need a little extra time because it's a lot of text to read. I see 19. We could do a few more. Okay, 24. One more to go, and then I can tell you which ones are the correct answers. There we go. So here are your votes, and as always, let me lock it now. So the first statement says that the suffix array lists the start indices of the leaves in left to right order. Now, left to right, as I said before, if you draw the tree in the normal way and not tilt it to the side like I did. But that's correct. If you order the children of every internal node in the suffix tree so that the edges are sorted as well. You have to do this in a trie. You don't usually insist on this. A tree doesn't have to be ordered in that sense. But for this correspondence to hold, it's necessary. This suffix, well, t starting at LR is the path label in T to the leaf storing R. That's not quite correct. But a slightly different statement is correct. This is the path label to the rth leaf in T in left to right order. The leaf storing R, well, that's the suffix starting at position R. That's a different beast. Okay, these can sometimes be the same, but they are not in general the same. Different way of saying this, TLR, so the suffix of T starting at position L of R, is the rth smallest suffix in lexicographic order. That is correct. That's the same as saying as the first statement if you want. The next one's an interesting one. It's not correct. If more means strictly more. In terms of the theta class, if you ignore constant factors, then the suffix tree and the suffix array need the same amount of space. The difference is only in the constant factors, but the factors are substantial. So in a sense here, the theta classes are betraying us in this instance. They don't really give us the interesting distinction here. But it's true, the two have the same theta class in terms of space. And the last question, L and T, well, one of them suffices to solve the text indexing problem. That is true because we defined the problem as supporting efficient searches for patterns. You can be, what efficient means, maybe you can be Catholic about this, but I marked it as correct because a running time of log n times m is very efficient compared to the n times m. Log n is much, much smaller than n. So this in practice is very efficient. Okay. If you have more questions about the definition, then please use the Q&A. Other than that, yeah, keep in mind this this definition here, the one that also most people voted for. Think of the suffix array as storing what's the rth smallest in sorted order. I'll later have another picture how to remember these things. We'll come to that. What I want to talk about next is how to construct suffix arrays. It's fine, we can, if we have the suffix tree, then we can just read the leaves from the tree. But I mean, hold on, we wanted to compute the tree and didn't know anything except my statement that there is a magic black box that does it. But we want to dig into this. So relying on suffix trees to construct suffix trees, that sounds like it's not going to work. But we now have a much simpler object. Instead of this complicated tree, we just have a sorted list. And sorting is something we know how to do. So we could just take all the suffixes of t, put them in an array, and send that to your favorite library method for sorting. Use the Java sorting method. That's a handful of lines of code, very easy to do. And it's for small examples not even that bad, but it can be very slow. And the reason is that if this is a general purpose sorting method, it relies on pairwise comparisons. And comparing two strings essentially means comparing them letter by letter. And in the worst case, you have to scan the entire two strings before you find which one's smaller. And well, if they differ, and if so, which one is smaller. Because we're talking about suffixes here and we always have the end of word marker, they will always differ. They cannot be equal, we know that. But because suffixes are potentially as long as the text or just slightly shorter, this comparison is very expensive. So we might need n squared log n time in the worst case, and that is a bit slow. Now, what can we do? We can do much better in two ways. The fancy version that we will just start looking at today and finish off tomorrow. But we can also do something that gets us a fairly long way and is much simpler by just exploiting that we're sorting strings and not arbitrary objects. And this is what I want to talk about first. I call this fat pivot radix quicksort. That's a fancy name for a fairly simple idea. You remember a quicksort. Quicksort was essentially taking a pivot element, and then you take your list and partition it into classes that are, well, by comparing with the pivot, you can have elements that are smaller and bigger. Here we do something slightly more refined. We don't split everything into smaller and bigger. We split it into three groups, and we look at just the first character of the pivot. So this first list is all the strings that have a smaller character at the first position than the pivot. B and A are both smaller than S. And the last list is the same thing, but now with the strings that have a letter that's bigger than the first of the pivot. And then the middle list is all the strings that have the same first character as the pivot. And this is all that we do. We never, in this radix quicksort, we never go beyond the first character. We don't do a full comparison until we can decide it, but we allow to keep these equal results for now. And fat pivot just means this is essentially the fat pivot partition. These are all equal to the pivot if you only look at the first character. And the rest is just as in quicksort. You recurse with the same idea, keeping track of which position you have to check next. So the important point here, that's why I grayed the S out. The important point here to remember is in this middle partition, these were all the strings that had the same character as the pivot. That also means they all have the same first character. So we can ignore the first character for now. We know it's equal. They have a common prefix. And we start comparing with the next character. Okay, let's see how this continues. We have this little tiny list. We do the same process with this pivot. So, well, these are obviously in the wrong order. Sorting is hard. Apart from that, this is an easy case because we end with two lists of just a single element, so we don't have to further recurse. Now we split the second list. This is more interesting. We pick the pivot she, and we're looking at the second character now. So there's a couple of strings that have a smaller character than H. there's one string that has a bigger character than h, and there's a couple of strings that have the same character as h. And now look, what happens here is in this list, well, we as human, we see these all have the same second character, but the algorithm doesn't know that for now. It only knows that they all have a character that's smaller than h, but we still have to compare this. So we're still looking at the second character in this string, in this sublist. Whereas here, this is the partition that had the same character as the pivot. So here we know these are all h, so we can advance to the next character in this list. And again, in the last list, something funny happens. This happens to be the same characters, the same strings, but the algorithm doesn't know it. It uses the next pivot and finds that the first characters are equal, so it only produces the equal partition. But that's where it stops. Then the next round of recursive calls splits the non-singleton lists further up. So we have a pivot here, and it turns out, as we've seen, all of these have the same second character. So they all just move to the next position. There's no splitting going on. And for this list, we have one that's bigger and the others move on to the next. I think I made a mistake. This should be done. We're looking at the L and we're looking at nothing here. So sorry, I goofed in this example. This should have moved on. And in the last list, we again find only equals, so we move on to the next position. And here we do this one more time. We partition around this. There's a couple of strings that have a smaller third character, and there's some that have the same. So here we move on to the next position. And here I just I should have omitted this this one step, but now comes the right version. So we move past the last character in the pivot, really. So this is, we fill that with dollars in that case. And well, again, this should have been here. I don't know, something went wrong on the slides, I think. And with these, I'll fix the slides for that. But so here we scanned past the entire strings in both cases. That's where we notice that the two are actually equal. But we have to scan the entire strings for that. And one more here. So here we have to continue with the pivot. Again, we find these are all the same, so we move to the next position in the string. Same happens for these, and these two are the same. So what we did is quicksort, but we partition only on the dth character. And initially d is 0, but then it gets bigger in the middle partition. We create 3 segments, the strings that are smaller, equal, or larger in this dth symbol, and we recurse, where in the middle recursion call we increment d. So in code, this algorithm looks very, very similar to quicksort and is very easy to code. An important observation here is we never compare equal prefixes twice. If 2 strings have a common prefix, we will compare that. We will have to find out that they have different, they have this shared prefix. But we never scan them several times. And this is what made the direct call to a string method slow. Someone's saying that the video stopped. Seems fine on my side, so I'll continue. Because we never compare the same, well, the other way around. For a standard sorting method, we repeatedly compare strings, and it could happen that we compare the same shared prefix many times, and we have to scan over this many times. Okay, so if your video has stopped, refresh, but if you can hear this, then it hasn't stopped, so it's not very useful that I'm saying this. What we can say about this fat pivot radix quicksort is that for a certain model of strings, if the strings are random, then we only need n log n time instead of the n squared log n that a standard sorting method might have in the worst case. It's very simple to code, and well, this expectation is about the choice of pivots, but it works for all texts. So if you choose random pivots, you will usually see behavior in this realm. It's very simple to code. It's very efficient for sorting strings, even if they're not suffixes. And we can also apply it to find the suffix array in n log n time. That's already quite good because we started with something quadratic. Reducing that to n log n gets you most of the way. Because it's so easy to code, it might actually be a method of choice if it's not a performance critical application. But still, sometimes this is still a bit too slow, and from a theoretical perspective, it's more time than we need, because we can actually do linear time, and this is what we'll look at in the next subsection. Before we continue with that, I think it's time for a small break while I'm trying to get an empty page. Well, it doesn't matter. Just ignore that this is already written here. Okay, I should have used the other page. Let's take a break till just a couple of minutes. Just 3 minutes, because I want to get the first part of the next section done for today. Good. See you in a few minutes. I'll add you the time that I have. Take a little breath, and then we'll continue. As always, if you have questions, put them into the Q&A. Then we can discuss that before we move on. All right. 12:11 on my watch, and sorry, that was a short break, just 3 minutes, but maybe just enough for a little breath, and we have some time to finish the first part of this next section. In the next subsection, I want to discuss how to compute the suffix array of a string in linear time. We've seen a simple n log n method using the fat pivot radix quicksort, which is actually very easy to implement and gets the job done in a reasonable time. But the theoretically best possible is linear time, and for that we have to work a little harder. Before we can describe this algorithm that gets the suffix array computed in linear time, I need to introduce the inverse suffix array, because it turns out the algorithm is easier to understand when we compute the inverse suffix array, and then can go back and forth between that and the suffix array itself. Conceptually, the inverse suffix array, this array R, is a very simple thing. It just says find me the inverse permutation that is encoded by the leaf array. Something I haven't stressed before, the suffix array is actually a permutation. So it stores the numbers 0 up to n in an array of size, in an array of 0 up to n. And it stores every number exactly once, so it just permutes these numbers in some way. And every permutation is invertible. There's an inverse permutation, and that one's stored in R. That's one way of expressing this. The other way of saying it, whenever we have that the rth leaf in the left to right order, the rth leaf in sorted order starts at position I in the text, then R of I is little r. And another way of saying this is that the suffix starting at position I has rank R, because there's R suffixes that are smaller than it in lexicographic order. So that's why I chose R for the inverse suffix array, because it's reminiscent of rank. And that's what it is. It stores the rank for the suffix starting at a position, whereas L stores the leaf in the left to right order, so where the suffix started. It's also, if you want, the left index of the suffix. And this picture below is, I think, a good way to memorize these two notions and to keep them separate, because I personally tended to mix those up easily, so this is also for myself. If we have a text banana bin, we write all the suffixes in text order, where we just move the next character, so you have this nice triangle shape. If you have this here, then I is just the numbers 0 up to 9. That's the starting position of the suffix. And then R of I tells you the rank of this suffix in the sorted order, lexicographic order. So the first one is actually always the one that's just the dollar by definition. But then the next one, who comes first, that's depends on the text, and in this case it's the suffix starting at position 5. On the right, I have the same suffixes, but now sorted lexicographically, whereas here things are in text order, how they appear in the text. And having the suffixes in sorted order means that the rank goes from 0 up to 9 in just counting up. And then the suffix array tells you where's the starting position of that suffix. So the smallest suffix in the text starts at position 9, it's just the dollar, and so on and so forth. And you see it occasionally happens that those two numbers match, but in general they don't. The second smallest suffix starts at position 7, for example. So those are the two things to keep in mind. Keep in mind this picture, the triangle on the left the jagged sorted list on the right. And then L and R have another nice meaning that luckily coincides. L means you are on the right and you want to go to the left. So it tells you where to find a certain string in the left picture. If you have the string here, Naban, it's the 8th in the sorted order. And then the L entry tells you that at position 4, you find the same string on the left. And same R, which I took standing for rank, can also mean right. If you have a string here, maybe the whole text, it starts at position 0, so that's this one here. If you look at R of 0, it tells you that's the 6th smallest, so it appears at position 6 on the right. Okay. I hope that these mnemonics stick in your mind and avoid you mixing up the two notions, the two concepts. Okay, if that is clear, then let's move on to the linear time algorithm for constructing suffix arrays. There's different algorithms that do this. What I will present is called the DC3, difference cover 3, or the skew algorithm. The name is a bit weird, but that's what got stuck. I don't want to explain where this comes from, really. That's just in case you're an expert and you see other algorithms. This is the one we will talk about. It proceeds in 3 curious steps. The first step is we make a recursive call and we compute the rank array, so the inverse suffix array, for some of the suffixes, but not all. Well, that wouldn't work. We leave out all the suffixes that start at a multiple of 3. So we recurse on 2/3 of the size, right, by leaving out every third. And obtain the sorted order. So R, again, the rank array, tells you, if you're given the starting position in the text, it tells you how many suffixes are smaller than this. Okay, that's the first step. How long that takes will depend on the other algorithm because it's recursive. We will see that eventually it is linear time, but that only follows at the end. The second step is, given that we know these ranks, we induce the ranks for the remaining suffixes. Now, in both cases, because we recursively call here, these ranks are only internally. They only rank how the suffixes are sorted within each other. And the same thing here, we essentially sort the list of suffixes, but only those that start at multiples of 3. And to speed up this sorting process, we use the information from R12. And finally, we have 2 sorted lists, so we merge them together, like in merge sort. And that will produce the rank array for the entire input. R, again, the rank array is the inverse suffix array, so if you have that, you can easily translate it to the suffix array. So that will construct L as well for us. Okay, now the magic here comes in showing that step 2 and 3 both run in linear time. Step 3, you might believe that this is doable because merging is usually running in linear time, but there's a caveat here because we're merging strings, and merging needs pairwise comparisons. So again, we have to speed up comparisons here in this third step for that to run in linear time. And for the second step, we're sorting. These are still n/3 suffixes roughly, right? So if we were to sort them with any simple means, it would take n log n time. We have to do it in linear time. So we have to use this information that we've computed recursively for that. And that will be the main trick of this algorithm. But let's first suppose we have already convinced ourselves that this is the case. what is the total complexity then for the recursive calls? Well, this is the step 2 and 3 on the top level. So we spend linear time here, linear time here. Let's just renormalize that so that the constant is 1. That's the top level. We make a recursive call, and now on this next level, we only have 2/3 of the strings. We will have another step 2 and 3, and they take together, they take 2/3 n. But that second step also has a recursive call, and it takes 2/3 of 2/3, and so on and so on. So you see, what we get here is this geometric sum. In every step, we get rid of a constant fraction of the input. So that means after we factor out n, we have this geometric series, and that is bounded by a constant, in this times 3. So that shows that the total cost is linear in n as well. Okay, so that is if the steps 2 and 3 take linear time, the entire algorithm takes linear time. That is a simple application of solving recurrences like you've practiced it in Unit 1. Also in the tutorials, or Unit 0, whatever it was. That proves that the entire algorithm is linear, but we have to show that these 2 steps can be implemented in linear time. Okay, that's just the remark. This algorithm actually computes R, but we can use it to compute L, and we can go back and forth between those. That's always doable in linear time. For the rest of today, I want to discuss this second step. So we assume we have, remember, the recursive call computes, sorts the suffixes, computes the ranks for the suffixes that don't start at a multiple of 3. And we would like to use that information to compute the other ranks. Okay. A little more formally, what I assume here, just to make the notation nicer, is that this array R12 contains the rank of the suffix starting at I among those ranks that are not multiples of 3, if I is such a not multiple of 3. And for the other ones, we just never access this. So what that says is just we spread out the array so that it doesn't use the indices at positions that are multiples of 3. That just makes the notation convenient. Now, our task is to sort this list of suffixes in linear time, and that looks like the same problem we originally started with. So it looks just as hard as the original problem. But here's the trick. Suppose we compare the 2 suffixes T0 and T3. These are very long strings. We don't have the time to compare them character by character. But what we can do is compare the first character, just one. And after we stripped off the first character in T0, there's some character and then a long remainder, but that remainder is just T1, the suffix starting at position 1. And the same thing happens for T3. There's some other character. I don't know if that's the same or not. We don't know in general. Okay, this is should be shorter. So that's T4 because we split off the first character. Now T1 and T4, 1 and 4 are not multiples of 3. So we can take their ranks from what we've previously computed and compare them by just comparing the ranks. That's the magic trick. By splitting off one character, we fall back into the set of suffixes that we know how to compare. And we can use that information to compare these other long suffixes that we didn't know anything about up to that point. So to summarize this, T0 comes before T3 in lexicographic order if and only if this pair as a small string, if you want, with the first character of T0 and then the rank of T1 comes before the pair where we take the third character of the first character of T3 and then the rank of the remainder. Okay, that's the main magic step, and that allows us to induce the ranks in constant time per comparison. So let's briefly look at how we do this in an example. Because there's one step that's still missing. We would still, I've shown you how we can do a single comparison in constant time, but we still have to sort. And doesn't sorting always take n log n time? Well, remember what we discussed when we were talking about the lower bound for sorting. It only needs n log n time if we don't know anything about the objects that we're sorting. And in particular, for small integers, we can sort in linear time. And this is where we'll come back here. We will use that as a black box here, but you actually know how it works. It's just counting sort. But let me finish with this overall picture here first. So this is the list of suffixes that we now have. And we want to sort them lexicographically. We recursively found for all the other suffixes, those that don't start at a multiple of 3, we found the sorted order. And in particular, we know this R12, the rank array. Okay. Now, what we do is, suppose we take this T15. We will transform this string, which is too long to sort efficiently, into something short that we do know how to sort efficiently. And the way to do that is split off the first character, that is just copied down. And then for the rest, S-man turns out to be, well, from T15 we go to T16. So we find that in this list. And in particular, we can look up the rank of this. So T16 is here. And on the other side, if we go to 16, we know its rank is 14. So what we put in here is a 14 as the second component of this pair. And we do that for all the suffixes that start at multiples of 3. And then we use radix sort to sort these in linear time, because they now consist of one character. That's even, if the alphabet is bounded, it's even a constant size. So this is very easy to sort. And the second component is a number that's bounded by n. And this we already know how to sort using counting sort. So that's this result here. We can sort these pairs in linear time by 2 iterations of counting sort. First sort by the second component and then stably by the first. That's how you would usually do this. And then we get the sorted list of these suffixes that start at a multiple of 3. And from that we can find the rank array. That's the second step of the DC3 algorithm. Given the ranks of the suffixes that don't start at multiples of 3, we could find the ranks of those that start at multiples of 3. One little caveat here is that these are ranks within that set. We still have to merge. We still have to do step 3. And that I will reserve for tomorrow. Okay, we'll continue tomorrow. Think of all the announcements. We had a couple of deadlines. We had the class test coming up on Friday, the videos half an hour ago. Make sure to get that in as soon as possible. Yeah, tutorials start tomorrow, so nothing on that front for today. If you have any questions, please feel free to ask. And if you want, I'm here for a little chat on Zoom if you have anything to discuss or just want to say hi after the couple of the break. As always, I'll take 2 to 3 minutes to clean up my mess from flipping the laptop over, etc. But I'll join in a few minutes if a few of you are interested. All right, cool. I hope you enjoyed this part. We'll continue tomorrow and finish this off, and see you tomorrow at 11 a.m. or if you want, in a few minutes on Zoom. Bye for now.